चल रही है कंपनी।
गुनवीर
पहले ब्लॉक में दुश्मन ये क्या करूँ? क्या हो गया? सब गायब। मसला 10 मसला क्लास में फर्स्ट क्लास की मतलब क्या है वेट करेंगे आप ऐसे एकदम बराबर 10:59 10:49 टाइम पर टाइम करेंगे हम जाएंगे ऐसा कुछ तो नहीं ऐसा ही है प्लीज एग्री ऐसा ही है क्या बताओ exactly 10 o'clock. If he sees you there, even though not allowed. If you are late, then you are out. धीरे-धीरे सारे क्वेश्चन में अटेंड कर होगा. Students are not attending the classes. Here it is compulsory. Still people are not coming. So until 2022, I never used to take the attendance compulsory. I have seen out of 180, 2 students are attending, and they all require notes. Notes and everything is required. Either I should not be giving any notes to anyone. Then people will attend, and if you are giving the notes, then they will not. Then the other way is you can make the attendance. That is the only way you can compel them to attend. So they will not attend, and at the end they will write, very good philosophical email. I like your quote. And he may start with that line. I like your quote. I am very much interested in this. And finally, towards the end, I am falling short of 1 attendance or 2 attendance. Please do. Start with that, okay? And I hate those philosophical emails. Okay. So people should be, saying it clearly instead of, that flattery I don't like. So we will wait for 1 minute, 1 or 2 minutes, and then we will start. So we will have tutorial today and one more tutorial tomorrow. Tomorrow is Monday timetable. So we will have tutorial in our regular time, same room. Okay. Okay, let's start with what we have covered in the last class. In the last class, towards the end, we started looking at the response of first order system when there is a sinusoidal. We said the sinusoidal input we wanted to understand more primarily because it's not the mathematics which is making us interesting in this particular solution. Instead of that, the real reason is frequency response is one of the methods which is used to find out the stability of the control system. In fact, frequency response is the only method which can give you the stability of the control system when the process is associated with dead time. This word is very important. When the process is associated with the dead time, then the only method to find out the stability of the control system is frequency response. And we will prove this particular statement as we go ahead. Okay. So when I am saying frequency response, what it means? Frequency response means we will be giving a sinusoidal input, and under the sinusoidal input we are observing my output. Okay, so this is what we call it as a frequency response. More details on the frequency response we will see towards the end of this course. Okay, but just to create a base, just to start with how the first order process is going to behave under the sinusoidal input. That is why we have started looking at this. Okay. So what we are saying here is first order process, as we have discussed in the last class also, first order process will be characterized by first order transfer function, which is given as भाई पीछे नहीं इधर सामने आ जाओ, ठीक है सब लोग. So first order process is characterized by a transfer function which is given as Kp divided by tau ps plus 1, isn't it? So transfer function by definition is nothing but what? भैया कोई लेटर वेटर चाहिए आपको डायरेक्टर की तरफ से, तब आप सुनोगे. आगे आओ, आप भी आप सुनो. So by definition the transfer function is given by what? Output in a deviation form, Laplace transform of output in a deviation form divided by
input
Laplace transform of input in a deviation form. So the transfer function is given by this equation, Kp divided by tau ps plus 1. Now we are assuming that there is a sinusoidal input, so f of t is given here. So f of t is given as a sin omega t. If I find out the Laplace transform of this input, what I am going to get? I am going to get a omega divided by s square plus omega square. Okay. If I rearrange this equation and multiply this f of s on the right hand side, what we get is ys. Ys comes out to be a omega divided by s square plus omega square. Kp by tau p divided by s plus 1 by tau. Now this equation has three roots. This equation has three roots, isn't it? You can see here this is degree 2, so you will have two roots here. So I can rearrange the denominator in the first term. I can write this particular term as s plus j omega and s minus j omega. Okay. And then again we can use the same methodology what we have done earlier. We can separate all the partial fractions. We can represent the partial fractions in this case c1 divided by s plus j omega plus c2 divided by s minus j omega and plus c3 divided by s plus 1 by tau t, isn't it? And then we can find out the constant c1, c2, c3 by using the method of partial fraction, and we can put it in the original equation and invert back into a time domain. This is what the expression we are expected to get. Yt comes out to be Kp into a omega tau p e raised to the power minus c by tau p divided by tau p square omega square plus 1. And the next term is minus a omega tau p divided by tau p square omega square plus 1 cos omega t plus a divided by tau p square omega square plus 1 sin omega t. I can combine these two terms. If I combine these two terms, what we get is this equation. Correct. So in this equation, you can see that the first term has e raised to the power minus t by tau p. And if I find out the ultimate response, if I find out the response at t tends to infinity, what I am going to get? This particular term is going to become 0, and we will get yt at steady state, which is given as a kp divided by under root tau p square omega square plus 1 into sin omega tau p plus phi, where phi is nothing but tan inverse of minus omega tau. Okay. So in this case, phi is nothing but a phase lag. Why I am saying it is a phase lag? It is a phase lag because there is a minus sign here. This minus sign will come out here. Isn't it? So you can see that the phase angle here is negative. Okay. Is it clear to everyone? Okay. So this is what we have seen in the last class. Then we have concluded that whenever we have a sinusoidal input, my output is also going to be sinusoidal. My output is also going to be periodic. Isn't it? And it is going to vary with the same frequency omega as that of the input. Isn't it? You can see that the steady state output, it also has the frequency omega, which is same as the input. Isn't it? However, the output will be lagging behind the input by a phase angle of phi. Also, if you look at the amplitude, what was the amplitude of input? Amplitude of the input is A. isn't it? But if you look at what is the amplitude here for the output, A divided by under root tau p square omega square plus 1, isn't it? This Kp is just a process gain which you are going to get in every response, isn't it? So in this case, if I divide the amplitude of output divided by amplitude of input, you can see that this additional term 1 upon under root tau p square omega square plus 1 comes into the picture, isn't it? You can see that the amplitude in this case instead of A, it is lower than that. Why I am saying lower? Because tau p is a positive number, omega is a positive number. If you multiply square of that plus 1, this entire denominator is going to be a positive number and more than 1. More than 1. Isn't it? And you are dividing a number more than 1 to A. So what will happen to the amplitude? Amplitude is going to decrease. It will not be same as A. Isn't it? So you can see that the output will have an amplitude lower than input. Lower than input. And that is why we are saying that the signal is attenuated. Okay? Now this entire thing we have derived here. I don't know whether you have derived this. I told you to derive. Have you? Why we are getting cos and sin terms? Because here we are going to get s plus j omega and s minus j omega. So why sin and cos? Because you will get a term e raised to the power j omega t and e raised to the power minus j omega t. That if you combine, you will get sin and cos. Okay? Is it clear? Then towards the end again we have seen this particular case study where we are looking at how the output of the thermometer is going to vary with respect to time. Isn't it? We said that let's say there is a thermometer which is placed in a water bath, let's say, and you wanted to find out what is the temperature of the water bath. Isn't it? This thermometer is not going to give you the temperature of the water bath instantaneously. It is going to take some milliseconds to give the value, isn't it? So it will start from its value and it will gradually increase or decrease depending on what temperature the environment is having, isn't it? And then after some time it is going to give you a steady state value, and that is what the value you are going to record as the temperature of the water bath. Okay, isn't it? And this particular dynamics between time t equals to 0 to a time at which you are going to get a steady state, this particular dynamics you can find out by solving the first order system. Okay. So what is been given here is, initially the thermometer is at a temperature T and you have suddenly put the thermometer into a water bath of temperature T naught, isn't it? T naught. Correct. And then you wanted to see how this temperature T is going to vary with respect to time. Eventually this will reach to the C naught, isn't it? But it will take some time. So that dynamics we wanted to represent by using equation. So in this case the energy balance we are going to make. Energy balance will be what? HA T naught minus C. This is nothing but the heat transfer from surrounding to this mercury here, isn't it? And based on that, the temperature of this mercury is going to increase, so that is given as mCp dt by dt. We can write this equation as steady state. That becomes HA T naught S minus Ts. If we subtract this from this equation, we will get an equation in a deviation form. Again, if we rearrange this equation, we get mCp by HA dt dash by dt plus T dash equals to T naught dash. This particular equation we can represent as a general equation of the first order process, which is nothing but tau p dy by dt plus y equals to kp into f of t. That is what the general equation is. We can represent it in a general form. So this is the general form we have represented, isn't it? If I take a Laplace transform and rearrange, we get kp divided by tau p is plus 1, same as the first order. In this case, tau p is the time constant which is given as mCp by ha, and kp which is the gain of the process, which is nothing but 1 in this case. Correct? Gain is just 1 in this case. Based on this problem we have solved in the last class. Isn't it? This problem we have solved. We said that suddenly the thermometer which is having a time constant of 0.1 is at a steady state of 90 degrees Celsius, we have suddenly put at 100 degrees Celsius. How much time it will require to give the reading 90? Isn't it? Correct? Now let's look at another problem. Please solve this problem. Okay? Please solve the problem. So what is given is a mercury thermometer having a time constant of 0.1 minute. It placed in a temperature bath of 100 degrees Celsius and allowed to come to equilibrium with the bath. And suddenly at time t equals to 0, the temperature of the bath begins to vary sinusoidally about its average temperature of 100 C with an amplitude of 2 degrees Celsius. If the frequency of oscillation is given as 10 by pi cycles per minute, what will be the amplitude of response and phase lag? So frequency is given. Frequency is given. What you have to find out? You have to find out omega, angular velocity you have to find. Okay. Frequency is given. So what is the value of omega? Anyone?
20.
2 pi f, isn't it? W is given as 2 pi s. F here is given, frequency is given as 10 by pi. So you can find out omega in radian per minute. Radian per minute. Yes, this is given in minute. So find out omega in radian per minute. Whatever you wanted to do, but I think in your calculator either you have to do it in radian or in degree. That is the only way you can solve. Then it's better to convert it into radian. Radian per second if you are asking, that depends on what is the time constant is given in minute. Isn't it? So if it is given in minute, better to find out in radian per minute. Correct. कितना है आंसर? ओमेगा कितना है? 20 रेडियन पर मिनट. एंड देन फेज लैग एम्पलीट्यूड कितना है? 2 बाय एंड फेज लैग so amplitude is given as 1 upon under root tau p square omega square plus 1, isn't it? So a divided by under root tau p square omega square plus 1, so that comes out to be 0.896 degrees Celsius. Isn't it? This is the amplitude of the response. Remember, amplitude of the input is given, which is 2, and phase lag is given as tan inverse of minus omega tau p. Here, when you are finding out this phase lag, make sure that you use the consistent unit. So in your calculator you have to change the mode to radian or degree, and based on that you have to use the values correspondingly, isn't it? Otherwise you will end up with getting erroneous results. Okay. So phase lag in this case comes out to be minus 63.5 dB. Okay. Coming back to the another question. I think we have already discussed the solution of this question. What is being given here is consider a process whose output exhibits first order behavior to input changes. So this is the model equation we are getting, which is tau p dyt by dt plus yt is given as kp f of t. This is the standard expression for the first order process. Correct. Now the values of the time constant tau p and static gain kp are not very known. They are not known to you, isn't it? Develop an experiment whereby changing ft in a certain way and recording the values of yt with respect to time, you can compute the values of unknown parameter tau p and k. So how you can do that? That is what you have to write. Only 3 steps are here. What will be the first step? This was the question I have given in way back 2014 or something. It was one of the questions given in the quiz, in the minor. So what will be the steps here? So the first question we have to answer how we wanted to vary f of t. Remember, f of t is the input. Input is how you wanted to give the input. Remember, in this case you wanted to find out tau p and kp. That means this input you have to give manually with your own discretion, and based on that you are going to record the output value. Correct. So what input you wanted to give? If you give a step input, isn't it? So if you give a step input, then we start with the point saying that let's give a step input. Then so you are going to give a step input, let's say f of t of a magnitude, let's say a, magnitude a, correct? And then you are going to record the values of y in t domain with respect to time t, isn't it? Time t equals to 0, time t equals to 1 minute, 2 minutes, 3 minutes. In this manner you are going to record the values of yt, and you are going to get a curve. You will get a curve, and how that curve will look like? The curve will look like this. Will become a constant. You start and then it will become constant. Exponential increase. That is what you are going to get. Isn't it? So once you get this curve, then after that we have to find out kp and tau p. So what will be tau p? At 63.2% of the ultimate response, whatever the time comes at that is the time. And kp, whatever the ultimate value you have obtained in the graph, that ultimate value is nothing but what? That is nothing but the steady state value of the output. So change in the steady state value of the output divided by change in the input, that is nothing but kp. In this case, if you are taking the variables in a deviation form, let's say the ultimate value comes out to be b. In this case, ultimate value of yt comes out to be b. And what was the magnitude of a? What was the magnitude of f of t we have given? A. Isn't it? So b by a will directly give you k. B by a will directly give you k. So only 3 steps are required. These are the 3 steps. Let ft change the step change of magnitude a, record yt for t greater than 0 and plot it. And then let be the value of y for t tends to infinity, then kp is given as b by a and tau p is given as t star. And t star is nothing but this is the time at which this yt becomes 0.632 of the ultimate value t. Okay, is it clear to everyone? Yes, no?
Sir, for example, if you are taking, in this case, it was given a pure capacitative process, then you won't be getting.
Your process is not there because in your capacity process, this term is not there.
Okay.
So this is the First order process. There is no
And
pure capacitive
There
process.
we can give impulse input also. Or
Impulse input also you can give, and with impulse also you can make the procedure. Even that is correct. If you give the impulse, but is it how easy to give a impulse input? It's not easy. Isn't it? Instantaneously you are increasing the signal and then making it zero. That is not easy to give. So that is why a better signal in this case, better input signal is a step input. You can do the same analysis even with the impulse input. That is possible. Okay? Is it clear? Okay. Okay, so let's start with the new topic. New topic is second order process. Remember what was the first order process? First order process is the process which is characterized by first order differential equation. Similarly, the second order process is the process which is characterized by second order differential equation. Okay. So in this case, if you look at this is the generalized second order differential equation, you can see a2 d square yt by dt plus a1 dy by dt plus a0 yt equals to d f of t. Let's assume that this a0 is not 0, isn't it? And if I rearrange the term, I can divide this entire equation by a0. So a2 by a0, we are defining this term as tau square. a1 by a0, we are defining this as 2 zeta tau. And b by a0, we are defining this as a kp. Here tau is a time constant of the second order process. Zeta is a damping factor of the process, second order process, and kp is the process gain. Please listen carefully that the time constant of the second order process is not related with the speed of response. Okay, don't use the same generalization what we have seen for the first order process. Remember, in the first order process, tau p or tau is a time constant of process which is related to the speed of response. But unlike that, the time constant of the second order process is not related to the speed of response. Instead, it is nothing but the natural period of oscillation. And these two words are very important, natural period of oscillation. I will explain why we are calling it as a natural period of oscillation. Okay. So time constant of the second order process is related to the natural period of oscillation. Natural period of oscillation. Okay. The another term which we have defined here is zeta. Zeta is a damping factor, isn't it? So damping factor is very, very important because based on the damping factor, your response is going to vary. If your damping factor zeta is greater than 1, then we get a overdamp process. Overdamp process, we have a exponential response like this. There is no oscillation. But when zeta is less than 1, you will see that your output response is having oscillation. So that is called an underdamped. And when zeta is equals to 1, then we call the process as critically damped. In a critically damped process, you don't get the oscillation. Okay, is it clear? There is one more thing. When zeta is 0, in that case we call the process as undamped. And whenever zeta is 0, it is not mentioned in your book, but when zeta is 0, then the process is called as undamped. In that case, you get sustained sine wave. In an underdamped process, you get a periodic response, but those periodic responses are going to die with time. So these variations are going to die out with time. But in an undamped process, you get sustained sine wave. So what it means? When I get an undamped process, what it means? When we get a sustained sine wave, we get a sustained sine wave whenever our roots are located on the imaginary axis. Isn't it? That's what it means. Okay. Alright? Okay. So if you apply the Laplace transforms to this equation, my transfer function comes out to be kp divided by tau square s square plus 2 zeta tau s plus 1. So this is the generalized equation for the second order process. Okay. And this particular expression is very, very important primarily because whenever we are going to look at second order process, we are going to write this equation directly. We are not going to model it and then write. No, we are going to directly write this. So second order process will have a transfer function like this. First order process will give a transfer function as Kp divided by tau ps plus 1. Second order process will give a transfer function as Kp divided by tau square s square plus 2 zeta tau s plus 1. Where tau is the time constant of the process and zeta is a damping factor. Kp is the process K. Is it clear to everyone? Yes, no? Okay. So we said that when zeta is less than 1, it is underdamped. When zeta is greater than 1, overdamped. Maybe I will draw it so that becomes clear. So if you give a step input to this process, the output what we are expected to get in this case, depending on the zeta value, so typical response which we are expected to get, let's say this is the zero line. So when we are having zeta greater than 1, in that case my system response is like this, for a step input. When my zeta is less than 1, which is a underdamped process, in an underdamped process my system response is going to be like this. Okay, and when zeta is equals to 1, which is nothing but critically damped, for a critically damped case, my system response is going to be like this. Okay. So this is for zeta value greater than 1, this is for zeta value less than 1, and this particular case is exactly for zeta value equals to 1. Okay, and what I am plotting here, I am plotting y of t versus t. Okay. If I plot yt by akp, if I plot yt by akp, in that case it will vary from 0 to 1. Okay, is it clear to everyone? Is it clear to everyone? Now look at the term here, undamped, overdamped and critically damped. The word damped is used. Isn't it? So this damped word is used in the context of oscillation. So when the oscillations are not there, we are calling it as a overdamped. When it is just at the onset of having the oscillation, that is critically damped. It is not there, but if you further decrease the value of beta, then we will have, isn't it? And when zeta is less than 1, then we are going to have the oscillations like this, isn't it? And what will be undamped? Undamped process will be again faster than this. Okay. Undamped process. So this undamped process will be something like this, but it will not die out. We will have a sustained sine wave. This sine wave is not going to die. That is called an undamped. Okay. And undamped process we have a zeta value equals to 0. Zeta value equals to 0. Correct? Is it clear to everyone? Okay. Now the important thing to note down here. Okay. So second order process. There are 3 types of second order. First second order process which you get whenever there are multiple first order processes are in series, which is called as multi-capacity process. Okay, so whenever we have a multi-capacity processes, what it means is multiple first order processes are in series, isn't it? So each of these capacity will give you first order process, and since these multiple first order processes are in series, typically you get second or higher order process. If there are two capacities, in that case you will get second order process. If you are having 3 capacities, you will get third order process, isn't it? You can have order, it can be any value, n, isn't it? Typical example is distillation column. In a distillation column, each tray act as a one capacity. So each tray will give you one differential equation, isn't it? Correct? And whatever the output from that tray is, that will be given as the input to the next tray. So if you look at this connection with each other, actually you get a nth order process. You get a nth order process. Okay, is it clear to everyone? So this is something called as multi-capacity process. So whenever two or more capacities are in series, then we get second or higher order process. Another interesting thing to note down here is, whenever we have a multi-capacity process, we always get overdamped process. We always get overdamped process. We never get underdamped process. We can get overdamped, or at max we can get critically damped process. We will not be getting underdamped process whenever multiple capacities are in series. Please note down this. We will prove this. We will prove this. Okay, there is a reason why I am saying. It's not that arbitrarily I am saying. Okay, all right. The second type of process is inherently second order process. Remember, in the starting also, I think 2 or 3 classes before I have said this, isn't it? So inherently second order process you get whenever there is a inertia associated with the process. So there are some moving parts are there. Typical example is spring and dashpot. And spring and dashpot, this particular system we don't see in the chemical engineering regularly, but in mechanical engineering we see. Okay. So whenever we have a process in which there is the inertia and the resistance to this inertia, isn't it? In that case we get inherently second order process. A typical process which we see in chemical engineering or process engineering with respect to this is mercury manometer. Mercury manometer, which is used for measuring the pressure inside the pipeline, it gives you inherently second order. We will see the proof of that as we go. Another example of inherently second order process which we see in chemical or process engineering is diaphragm wall. So remember, most of these walls are having the diaphragm, isn't it? So all these diaphragm wall can give you inherently second order. Okay. One more thing to note down here is this particular case study we have seen, isn't it? This particular example we have seen. What is the process? First order. But this first order process is subjected to these 3 assumptions. If any of these assumptions you remove, you will get second or higher order. For instance, in this case we have assumed that the entire heat capacity is present only in the mercury. There is no heat capacity associated with this glass wall which is there. Also, we are not assuming that there is any resistance to this glass wall. We are assuming that all the resistance is present only in the thin film which is outside of this glass wall. If you assume that there is a resistance in this thin film as well as there is a resistance in this glass wall, you will get a second order process, not first order process. You will get a second order differential equation in that. Okay. So you can see that this particular system is a first order strictly with these assumptions. If you remove any of these assumptions, then the process is not first order, it is higher order. Okay. Another interesting thing to note down and another important difference with respect to the first order process here is, remember what type of response we get in a first order process. In a first order process, our response is exponential. So my response is something like this, isn't it? My response is something like this. Isn't it? My response is something like this. The difference between the first order process and the second order process is, in a second order process your response resembles to sigmoidal curve. It is S-shaped. So it is initially it is sluggish. You can see it is sluggish here in the initial. You get a S-shaped response when your process is second or higher order. Okay. But in first order process, it is increasing like this. So that is the difference. It is clear to everyone. There are small differences which you have to carefully note down. Okay. So inherently second order process we get whenever the process is associated with the moving parts and these moving parts are having inertia associated with them, then we get a inherently second order process. A typical example is spring and dashpot, where you can see that the spring moves and comes back. There is a moving part. When you are looking at mercury manometer, in a mercury manometer fluid is moving. There is a movement. When you are looking at the diaphragm position moves. So whenever there is a movement of the part associated with the process and the inertia associated with that, then we get inherently second order process. Okay. Another example of the second order process is, let's say I am having a first order process. A typical example is a stir tank heater system, and I am interested in maintaining the temperature inside the stir tank heater. So what I will be doing? I will be measuring the temperature. That measured temperature will be compared with the set point value in the comparator. That will give me the error. That error will be given to the controller, and controller, based on this error, it will use proportional controller or proportional integral controller or proportional integral derivative controller, and based on this, the controller is going to perform the control action by manipulating the manipulated variable, which in this case is nothing but the flow rate of the steam. Correct? So whenever a first order process is associated with its control, and that together, control system and the first order process, they may give you the second order. Okay. So that is the third case. You can get second or higher order process whenever you are having multiple capacities in series. That is case number 1. You can get second or higher order process whenever you can have a inertia associated with the process. That is something called as inherently second order process. And the third case is the first order process associated with its controller. Together they can give you second or higher order. Is it clear? Yes, no? All these three cases we will see little bit in more detail as we go ahead. Okay. So again, one more thing to note down is, whenever we have a multiple capacities in series, we always get overdamp or at max critically damped. We never get underdamped process. Underdamped process you can get only in these two cases, last two cases. Underdamped processes are possible only in these last two cases, not otherwise. Okay? Is it clear to everyone? Okay. Now let's look at the solution of the second order process when there is a, let's say, step input. So second order process, this is the typical transfer function which is given as Kp divided by tau square 2 zeta tau s plus 1. Isn't it? Transfer function is there. So transfer function is nothing but what? Laplace transform of output in a deviation form divided by Laplace transform of input in a deviation form. So that is nothing but ys by f of s. Isn't it? Now we are assuming that the step input is given. So that means what? This f of s is nothing but what? Let's say step input of magnitude unity is given. So f of s is nothing but what? F of s is just 1 by s. So I can multiply this f of s with this equation and I can get ys. So ys comes out to be what? Ys will be Kp divided by s and this entire term. Tau square s square plus 2 zeta tau s plus 1. Now what is the order of s here? In the denominator, order of s is 3. Isn't it? So 3 roots are possible. 3 roots are possible. Isn't it? One root is exactly an s equals to 0. And the other two roots depending on whatever the roots we get here. For a time being, let us assume that these two roots are P1 and P2. P1 and P2 are the two roots. Isn't it? Now, this particular term is there, which is nothing but a quadratic term. For quadratic term, we can find out the roots easily. Yes or no? So this quadratic term, what will be the roots? Roots will be given as minus zeta under root zeta square minus 1 by tau. You can directly find out. Remember, in this case, b is what? b is nothing but 2 zeta tau, and a is tau square and c is 1. Roots are given by minus b plus or minus under root b square minus 4ac by 2a. So we can find out the roots. Two roots in this case comes out to be minus zeta plus under root zeta square minus 1 divided by tau. This will be the root number 1. Root number 2, it will be same as this except this plus sign we have a minus. Okay. So these are the two roots, P1 and P2. Isn't it? Now again just for a simplicity. Simplicity. Why? Because if you rearrange the terms in this manner, then you can derive the solution easily. So let's assume that this entire term, this P1, if we represent this P1 as minus 1 by tau 1, and this P2 we can represent as minus 1 by tau 2. There are some mistakes in your notes which I have given. I am correcting some mistakes in between because all the notes I have prepared last year. These PPTs I have prepared last year. Okay. So at that time some mistakes are there which I am correcting. So the PPT which I am showing here is free of any mistakes. But whatever I have given you in a print, there are some mistakes. Okay. So please check carefully. So I think this is also given as 1 by tau 1 in your print. If I am not wrong anyway. Okay. So this type of mistakes are there because these are cut and pasted, and then remember all these PPTs are I have prepared from the scratch. It is not copied from the book exactly. These are written, all the equations are written from the scratch, and all the figures are made newly. These are not copied from the book. Okay. So there are some mistakes which I am correcting as we are going ahead. So mistakes are such minor mistakes because these are the mistakes because of cutting and pasting here and there. Because of that, somewhere the subscripts are missing, somewhere the wrong subscripts are given. That type of mistakes are there. Okay. So let's take this particular term as minus 1 by tau 1 and this particular term as minus 1 by tau 2. If you do that, this entire denominator we can represent like this: Kp divided by tau 1 tau 2 S plus 1 by tau 1 S plus 1 by tau 2. Correct? Now once we represent like this is a very this particular equation I can invert that easily, isn't it? Because now I can write this particular equation as C1 divided by S, C2 divided by S plus 1 by tau 1 and C3 divided by S plus 1 by tau 2. Correct? So C1 divided by S, what I am going to get? If I invert that into a time domain, I will get C1. Isn't it? Because the Laplace transform of 1 is 1 minus. Isn't it? So if I invert that into a time domain, I will get just C1 for this particular term. How about C2 divided by S plus 1 by tau 1? C2 into e raised to the power minus T1 minus T by tau 1. And similarly the third term will be plus C3 e raised to the power minus T by tau 2. And this C1, C2, C3 I can find out by partial fraction. So C1 comes out to be just Kp. If you find out the partial fractions, you will get C1 equals to Kp. C2 you will get Kp divided by Kp into tau 1 divided by tau 2 minus tau 1. That will be C2. And C3 comes out to be minus tau 2 divided by tau 2 minus tau 1 into Kp. These are what? These are C1, C2, C3 you are going to get if you find out the partial fraction. That detailed derivation I have not worked out here, but you can do it easily. Now, the interesting point here is this particular derivation. This particular derivation is the most easiest derivation here, but it is not the only form of the equation which we are looking at. You will see that for second order process, you will get slightly more complicated equations. I will show you that in the next slide. Now this particular equation is valid. This particular equation is valid only in the case when tau 2 is not same as tau. Tau 2 is not same as tau. Because when tau 2 is same as tau 1, in that case you get zeta equals to 1. In that case this is not valid. This is not valid. What it means is if tau 2 is equal to tau 1, in that case you can see that this particular equation, in this particular equation zeta is going to become 1, isn't it? Zeta is going to become 1, and if you find out the roots here, the roots will be what? multiple roots you are going to get. Tau s plus 1 square you are going to get. So s is given as 1 by tau minus 1 by tau. That is what you are going to get. Okay. Okay. So remember I said that was the simple derivation, but you can get a complicated derivation. For example, if you are taking, let's say, the example of second order overdamped system. The overdamped system has zeta greater than 1. And if you start solving in the original form, if you start solving this entire equation in the original form, what derivation you are expected to get is this. This is what the derivation you are expected to get. Yt given as kp 1 minus e raised to the power minus zeta t by tau cos hyperbolic under root zeta square minus 1 into t by tau plus zeta divided by under root zeta square minus 1 sin hyperbolic under root zeta square minus 1 into t by tau. So this entire equation you can get if you start solving in the original form. In fact, this equation also you can derive from this. You can derive from this. How? Because remember tau 1 and tau 2 are given in the form of beta. This is the tau 1 and this is tau 2. I can put this tau 1 and tau 2 in this particular equation and simplify. Ultimately, you will get this. And why we have represented this in terms of cos hyperbolic and sin hyperbolic? Primarily because this particular term we wanted to get as a positive term. Remember, in this case, zeta is greater than 1. So this under root term is going to be positive. Correct? We can get a similar expression where zeta is less than 1. In that case, instead of sin hyperbolic and cos hyperbolic, we will get the solution in terms of just sin and cos. And this under root term will be 1 minus zeta square. Okay, is it clear? So that type of small rearrangement we have to do depending on whether the process is overdamped, underdamped, critically damped. In a critically damped case, zeta is just 1. In that case, you get slightly different solution. Why? Because you are having multiple roots, and whenever we are having multiple poles, what type of solution we are expected to get? 1 plus t by 1 factorial, 1 plus t by 2 factorial. That t term is going to come additionally. So all those additional terms we are going to see in the next class. We will stop here. Okay? Is it clear?
खाना कर रहा है इसके